Hello, and welcome to Optimizing in a Strategic World, an invitation to algorithmic game theory. My name is Richard, and I will be in the background answering any WebEx technical questions. If you experience technical difficulty at any time during this WebEx event, please submit your technical issue in the chat panel, and I will assist you. You may also contact our WebEx technical support at 1-866-779-3239. Please note that as an attendee, you are part of a larger audience today. However, due to privacy concerns, the attendee list is not displayed. All attendees will be in a listen-only mode for the duration of today's call, and as a reminder, this call is being recorded. We will be holding a Q&A session at the conclusion of today's presentation. You may ask a question at any time throughout the event by entering it into the chat panel at the lower right of your screen. If you do not see a chat, make sure the circle with the chat bubble is either blue or orange located at the bottom of your screen. If it is not, please click on the circle. And with that, we invite you to sit back, relax, and enjoy today's presentation. I'd like to introduce you to our first speaker for today, Sheila Castaneda.
Hi, everybody. And we're so glad you could join us today. We're really fortunate to have our speaker is Dr. Anna Karlin from the University of Washington today. This will be our 18th virtual undergraduate town hall. And we've been having some great topics. Today's topic is about algorithmic game theory. So I think you're going to really enjoy it. I had a chance to look at the slides before today, and they really look interesting and fun. Our speaker again is Dr. Anna Karlin. As you can see from her bio here, she is a very distinguished and experienced researcher that has done lots of great things. Anna also is on the CRA-W committee. I'm a member, and so is Lori Pollack, who is also one of the organizers for the VUTH. So today, during Anna's presentation, she's going to have some polling questions, and you'll see those at the bottom of your screen. So please participate. We want your feedback. And Anna will work those into her talk. And you'll see at the bottom also is the chat box. And so we encourage your feedback, your comments, your questions, and we will be feeding those back to Anna, or we will try to answer them as we go along. So participate, enjoy the presentation, and I'm going to turn it over to Anna now.
Hello, and welcome to this virtual undergraduate town hall. I'm Anna, and I'm delighted to be talking to you today. Just a couple words about myself. My research area is algorithm design and analysis, so one subfield of theoretical computer science, which is a wonderful field if you love math like I do. I have a family. There's my husband and I on the bottom left, and our two daughters. Actually, it's a very old picture because they're now both 19. And I guess at this point, I will just head into the technical material. So let me motivate what I'm talking about with an example. If you take Algorithms 101, you might learn about the maximum weighted matching problem. So in this problem, there's a weighted bipartite graph. So a graph where the vertices are divided into two sets and all edges go from one side to the other, and every edge has a weight on it. And the goal of this problem is to find a matching that maximizes the sum of matched edge weights. So in this example, the orange edges are a matching. A matching means that basically it's a set of edges that share no common endpoint. And the fact that it's a maximum matching means that the sum of the numbers on the matched edges is as large as possible. So if you take algorithms, you learn about how to design an efficient algorithm for this problem. Let's consider now a particular application where you might want to solve this problem. Suppose you have a search engine that has, or Facebook or something like that, that has advertising slots for sale. So in this case, the nodes on the left-hand side represent the advertisers. The nodes on the right-hand side represents ad slots. And the number on each edge represents how much that advertiser is willing to pay to have his or her ad shown in that slot. And if you think about it from the perspective of Google or Facebook, they might want to match advertisers to slots in such a way that maximizes their revenue, which would be exactly the maximum weighted matching. So here's the problem with this situation. We can't just expect that we'll be able to find this maximum weighted matching. And why is that? It's that these numbers on the edges, they come from the advertisers. The algorithm, or in this case, this Google or Facebook, asks the advertisers how much they're willing to pay to have their ad shown in this slot, and the advertisers report a number, okay? And they will certainly not report the truth if by not reporting the truth, they can get a better deal. So for example, here, if they knew that we were going to run a maximum weighted matching algorithm, then this advertiser who reported a 5 would rather just report a lower number, for example, 3, because they'll still get the slot they wanted, but they will essentially have saved $2, okay? So that benefits them quite a bit. And in order for an advertiser to figure out what they should tell the search engine about, how much they're willing to pay to have their ad shown, they have to speculate about what all the other advertisers are doing and reporting. And this becomes a very complicated and difficult thing to predict what will happen and how close Google or Facebook are getting to the maximum possible revenue, okay? So this is one of many problems where the input to the algorithm is the private data of agents that will act selfishly to promote their own best interests. So whether it's an online auction, such as those used by eBay, or ad auctions, such as those run by Google or Facebook, or peer-to-peer file sharing, or routing, or scheduling, or video streaming, resource allocation, where you have a set of resources to be shared among different entities, routing and congestion control, any electronic commerce setting, the input is coming from agents who have a selfish interest in the outcome of the algorithm or protocol. And that's not what you're taught about when you take Algorithms 101. So the fundamental question we look at in this research area is how do we optimize, how do we solve optimization problems when we have to deal with strategic behavior? How do we design algorithms that take incentives into account? And the approach is to use ideas from game theory and economics. So in this talk, I'm going to start by giving you a brief background in game theory, and then I'll try to briefly survey two of the major research areas that are very active right now in this area. So this is kind of at the intersection of algorithms and game theory and economics. So let me start with a little bit of background about game theory. So game theory is about games. Now you all know that you've played games, so you've played Go and chess and whatever it is you happen to play. What game theory does is it studies the behavior of players in strategic settings. It asks, if we have a set of players, each with a set of possible strategies, each motivated by self-interest, what do we expect to happen when they play the game, okay? So let me illustrate this with a simple example. If you saw this old movie by James Dean, which you probably haven't because you're too young for that, but at some point in that movie, there's two people who play a game called Chicken. And in this game, you have two drivers that are driving towards each other and towards a very narrow bridge. So we're going to represent this game by a matrix. One of the drivers is going to be the row player. One of the drivers is going to be the column player. And each of them has two strategies. One strategy is to drive straight onto the bridge. The other strategy is to swerve off before they get to the bridge. And the entry in each position in this kind of matrix here tells you the payoff of each player depending on the strategy the row player and the column player choose. So for example, if they both go straight onto the bridge, then they each have a payoff of -5. This is basically because they're going to have a head-on collision. So you might think of this as a very bad outcome. Negative means bad, okay? if they both swerve before they hit the bridge, then nothing really happens, and they both have a payoff of 0. But if one of them swerves and one of them goes straight, then the one who swerves is a chicken. So the leftmost entry here is the payoff to the row player. The right entry is the payoff to the column player. And the chicken has a payoff of -1. The one who went straight has the payoff of +1. So this little matrix defines a very simple game, okay? Now, suppose you and I are playing this game, and I'm the row player, and you're the column player. And suppose you knew I was going to swerve. What would you do? Would you A, swerve, or B, go straight? I guess you should try to answer the question if you're out there. Okay. I'm not seeing the answers, but are there answers? Or? Okay, well, aha! Most of you said straight, which is exactly right. Of course, if you know that I'm going to swerve, you're better off going straight because then you have a payoff of +1 instead of a payoff of 0, okay? And similarly, I think we'll skip the poll on this one if we can. If I go straight, then you're better off swerving because then you will have a payoff of +1 rather than -1, okay? So basically what we just talked about was what your best response is to what I might do. And this is one of the basic ideas that we study in game theory. We study the concept of an equilibrium, how we expect each player to behave. Now, there's many different notions of equilibrium. One notion is the notion of dominant strategies, and that means that each player has a best strategy no matter what any of the other players do. So you might have a best strategy of always swerving, or you might have a best strategy of always going straight. But is that the case in this game? Does this game have dominant strategies? Do you have a single strategy that you want to use no matter what? Well, I think I'll give you a second to answer that question. Sorry, I wasn't aware of the timing exactly here. But as most of you realize, you do not have a best strategy no matter what I do. As we just discussed, if I swerve, you want to go straight, whereas if I go straight, you want to swerve. That means there's not one strategy that you can always use that will give you the best response, okay? So because most games don't have dominant strategies, meaning that in most games your best response does depend on what the other player is doing, the next important notion we have is the notion of a Nash equilibrium. And a Nash equilibrium is when each player, there is a pair of strategies, let's say one for the row player and one for the column player, where each player is playing a best response to what their opponent is doing. So in the game of chicken, as you've already essentially observed, we have two possible pairs of strategies that are Nash equilibrium. If I swerve and you go straight, that's a Nash equilibrium. Why? Because you're playing a best response to me and I'm playing a best response to you. And similarly, if I go straight and you swerve, that's also a Nash equilibrium. So we might expect a game to end up in a Nash equilibrium. Why might we expect that? Because we expect players to best respond to what the other player is doing. Okay, let's look at another example. This is called matching pennies, and it's actually a zero-sum game. It's called a zero-sum game because the sum of the payoffs adds up to zero everywhere, meaning my gain is your loss and vice versa, okay? Now, in this game, this is a game where basically each of us has a coin that we hold behind our back, and we choose whether to put it on heads or tails. If we both put it the same way, like we both put heads, then you pay me $1, which means I gain $1 and you lose $1. If we make opposite choices, for example, I choose heads and you choose tails, or I choose tails and you choose heads, then I have to pay you $1. So that's how the game is defined. And you can ask the question whether or not in this game there's a Nash equilibrium. Is there some square here where each of us is playing a best response to what the other player is doing? And the answer, which I'm going to skip actually this poll, but the answer is that no, there is no such point. There is no square here where each of us is playing a best response. Why is that? Because if I play heads, okay, then your best response is to play tails, because that would give you +1 instead of -1. But if you play tails, then my best response is to play tails also rather than heads. And similarly, you can go through each box here and see that whatever any one, there's no square here where both of us are best responding to each other. However, we can extend the notion of Nash equilibrium and allow each of us to use a mixed strategy. What that means is that we choose what we do with some probability. So behind my back, I essentially toss a coin. If it comes up heads, I choose heads. If it comes up tails, I choose tails. And you do the same thing. And now I claim that what each of us is doing is a best response to the other. Why is that? Because if I play heads with probably 1/2 and you play tails with probably 1/2, then your expected payoff for heads is 1/2 times -1 plus 1/2 times +1, which is 0. And your payoff for tails is also 1/2 times +1 times 1/2 times -1, which is also 0. So you don't have any advantage playing one strategy over the other. And in particular, if you randomize, that is still a best response. So this is a situation where there is a Nash equilibrium as long as we're allowed to use randomized strategies, okay? So the early, most important results in the field of game theory were by two very, very famous mathematicians. The first result, and really the introduction of game theory, came with the work of John von Neumann, who's also one of the fathers of computer science, by the way. And he showed that every zero-sum game has a mixed Nash equilibrium, meaning there is a randomized strategy each player can use that is a best response to the strategy the other is using. And John Nash, who you might have heard about if you've seen the wonderful movie A Beautiful Mind, proved that this extends to more general games, games that are not necessarily zero-sum. So these are kind of the two starting points from game theory that we think about when we come back to our computer science applications. So let's turn now to using these concepts in a computer science application. And I'd like to tell you about some really cool work that was done on a topic called price of anarchy. So here, the problem what we're looking at was we're trying to explore games that arise in real-world systems, like resource allocation in the internet, or routing and congestion control, or ad auctions. And we're trying to understand the impact of selfish behavior, the fact that the different entities are going to act in their own best interests, on the performance of the system. Does selfish behavior hurt the performance of our systems relative to what would happen if we could force each of the participants to do what we wanted them to do? So let me illustrate this with an example. And this is some work due to Roughgarden and Tardos on selfish routing that I would like to explain to you because it's super, super cool and it's easy to understand the starting point here. So imagine I have a network, which is shown on the bottom left here, and I have a bunch of cars that are driving from point A to point B. And they have two routes they can take, one through C and one through D. The labels on the edge represent the latency that a driver will experience as a function of the fraction of traffic that goes on that edge. Okay. So the basic, in this example, the fact that the edge C to B is labeled with a 1 means that the latency on that edge is 1 no matter how many cars are using it. You can think of this as like a very wide highway where the congestion doesn't depend on the number of cars. Whereas the edge labeled X, the latency will depend on the fraction of traffic. So if 1/3 of the traffic goes on AC, then the latency on that edge will be 1/3. If 2/3 go on the edge AC, then the latency on that edge will be 2/3, and so on. Okay, so now if we think of our traffic, each driver, you can think of each driver as an infinitesimal fraction of all the traffic, decides which route to take. What do we expect them to do in Nash equilibrium? And by Nash equilibrium, let me remind you that what I mean is that given what everyone else is doing, each driver will choose the route that minimizes his own latency. Okay? So I want to claim that in this example, exactly half of the traffic will go on each route in Nash equilibrium. Okay? And why is that? Well, suppose, for example, that 2/3 of the traffic took the upper route and 1/3 took the lower route. Okay? Well, then the people that took the upper route would have a total latency of 2/3 plus 1, right? 1 and 2/3. Whereas the people that took the lower route would have a total latency of 1 and 1/3. So the people on the upper route would realize that given the current traffic, they should not have taken this route. They should switch to the lower route. So the only situation in which no one wants to switch what they're doing, the only situation where everyone is best responding to what everyone else is doing, is when they take each route, half the traffic goes on each route. Then the latency on both routes is the same. It's 3/2, and nobody wants to change what they're doing. Okay? All right. So now I want to show you something truly, truly bizarre that happens when you consider situations with strategic behavior. And it's called Braess's paradox. And what it kind of illustrates is that strategic behavior leads to sometimes very counterintuitive results. Okay? And so let's consider the following scenario. We started with the picture on the left. And suppose the government builds a new very, very fast highway from C to D. So fast that for all practical purposes, it takes no time to get there. Okay? So the government has just spent money expanding the capacity of the network. Okay? And the question is, how does this affect the average latency that the drivers experience in equilibrium? Okay? So my question now is, what is the Nash equilibrium in this new setting? And I think it will take a little too long for you to figure this out, so I'm just going to tell you the answer. But the answer is just crazy, okay? What I claim is that in equilibrium, in this new setting, all the traffic will go from A to C to D to B, all of it. And if all of it goes from A to C to B to D to B, then everyone experiences a latency of 2. So let me try to convince you why that's a Nash equilibrium, okay? So that's a Nash equilibrium because suppose that less than all the traffic took the edge AC, okay? Which means that some of the traffic took the path ADB, okay? So what that means is that anybody who took ADB would now do better by switching to ACDB because they would play less than 1 on AC versus 1 on AD, okay? And similarly, if some fraction of the traffic took took this edge, this one edge from C to B, then they would prefer to switch to the route ACDB because, again, it would have a lower latency. So I realize this is a little bit hard to understand in such a short amount of time. But if you draw yourself a picture of this and go sit for a couple minutes afterwards, you'll be able to convince yourself that the only equilibrium in this network, the only situation where everyone is best responding to what everyone else is doing is for everyone to go from A to C to D to B, which means that the average latency went from 3 halves before we added the extra capacity to a larger latency of 2 when we added the extra capacity. In other words, the government spent money and things got worse. And this situation, although this is a contrived example, this situation has actually been observed in the real world, where extra capacity was added to a road network and things actually got worse because it changed the way people choose where they drive. So this is an example showing that selfishness was hurt us. Okay, if we had forced half the traffic to go on the upper route and half the traffic to go on the lower route, we would have had an average latency of 3 halves. But because people were selfish, it went up to 2. And the Koutsoupis and Papadimitriou coined the name price of anarchy to capture this difference that can occur because of selfish behavior. So they call the price of anarchy of the system the performance in the ratio between the performance in the selfish equilibrium and the performance at the social optimum. And what they showed, what we saw in this example, was that this performance can be as bad as 4/3. Okay, that's what we got, was 2 divided by 3 halves, which is 4/3. So this was a tiny little example with 4 nodes and very simple functions on the edges. And you can ask the question, how much worse can it get if I have a much larger network like you would have in a real city and different latency functions on the different edges? Can it get much, much worse than 4/3? And surprisingly, it's been proven that it's never more than 4/3, no matter how complicated the network is, no matter what complicated linear latency functions you have on the edges, it's never more than 4/3. So that's actually very cool. It shows that the selfishness hurts us, but it doesn't hurt us too much. And various people, including myself, have studied the price of anarchy for a number of other kinds of games that show up in computer science settings and bounded the price of anarchy. And I will tell you that there are situations where it's much, much worse than 4/3. But I don't really have time to get into that. Let me just spend our last few minutes telling you a little bit about the area that I do most of my work in, which is algorithm design with incentives, which is called mechanism design in the microeconomics literature. But some of us also called it incentive engineering. So basically, this is kind of what I was telling you about in my example at the beginning. I'm a designer. For example, I'm Facebook trying to design an auction for selling ads, okay? Or I'm a road engineer and I'm trying to design, or the government trying to design a system of tolls on the roads. And I have some objective. Like if I'm Facebook, maybe I'm trying to maximize profit. If I'm the government, I might be trying to minimize the latency that everyone experiences on the roads. I have an objective in mind, like you have whenever you design an algorithm. And the question is, given that objective, can I design the game or the algorithm or the protocol? So in this setting, an algorithm or protocol becomes a game because the participants are strategic. Can I design it in such a clever way that even if the players act in their own self-interest, they will achieve my goals as a designer? Okay. And as is listed down here, 2 examples of this are designing a system of tolls on roads or selling ad slots on a search engine. And I should say that this business of selling ad slots on a search engine is the killer applications for this domain, because you may know that Google and Facebook and many of these companies, they make all their money on ads. So they work very hard to make money that way. And what that involves is some sort of game that they design in which the players are the advertisers, okay? And I don't really have time to explain to you the interesting theoretical and algorithmic problems that come up when you study this kind of thing, but that's been one of the subjects of my own research. I was going to tell you a little bit about simpler auctions. Let me see if I can try to do that. Okay, I'm trying to figure out if I have enough time. But let me just say a few words about suppose I just wanted to design an auction to just sell a single item. So this is like a super, super special case of the problem Facebook might be designing. So what they do is they have bidders, which are advertisers, and those bidders submit a bid which sort of says how much they're willing to pay to have their ad shown in a particular slot. And what might Facebook do? Well, one possibility is they just take the highest bidder, they put his ad in the slot, and they pay, and then that advertiser pays whatever they bid. And you can ask the question, is this a good way for them to auction off that ad slot? Okay? And if I want to study this question, I need to have a mathematical model in order to do that. And the mathematical model that we use is the following. We basically assume that these advertisers or bidders each have some private value for getting the slot. If your private value is $100, what that means is that you're indifferent between getting the slot and having $100 in your hand. Or if I gave you the slot for $80, it means that you would have made $20, right? Because that's how much more you valued the slot than what you paid for it, okay? So we think when we study these problems, we model the advertisers as having a utility, which is the difference between their value and the price they pay if they win the auction, and zero otherwise. And you can ask the question, what are these bidders going to do if I run an auction where I give it to the highest bidder at the price they bid? Well, clearly, they're not going to bid their true value. Why would they bid their true value? Because if they bid their true value, they will pay their true value and their utility will be zero. So what they'd really like to do is bid a little below their true value, low enough so that they make a lot of money, meaning the difference between their value and the price is large, but not too low that they lose the auction. And that's a complicated problem for them to figure out how to solve, because they have to speculate about what all the other advertisers are doing. So it turns out there's this beautiful result, and this is the basis for Google's ad auction, actually, but I'm giving you just a very simple special case, which is known as the Vickrey second price auction. And it says, let's do something else. Instead of having them submit their bids and selling it to the highest bidder at their price, let's have them submit their bids, but the highest bidder will still win, but that bidder will only pay the second highest bid submitted. So if the highest bid is 100 and the second highest bid is 68, then the highest bidder will win, but will only pay 68. And the claim I want to make is that you can prove, and I encourage you to think about this on your own, because it's not too hard to convince yourself, but you can prove that it is in each player's best interest to bid their true value, no matter what the other players do. And this has some wonderful, wonderful properties. It means that the advertisers don't need to strategize, because it's always in their best interest to tell the truth. It also means that since they are telling the truth, the slot or the item will end up going to the person that really truly values it the most. And perhaps most surprisingly, we can prove that in equilibrium, and that's a little bit more complicated in this setting, but in equilibrium, the profit of the seller using both these auctions is actually the same. Once you account for the fact that in the first when you sell to the bidder that bids highest at his bid, he's going to have to shade his bid down if he wants to make some money. So this is all super cool and super exciting. And I just will say just a couple words. Most of my own work has looked at mechanisms for profit maximization in more complicated settings than this single item auction that I just described. And what I've focused on is trying to avoid making the typical assumption in economics, which is that I, as a seller, know the distribution that the player's values come from. So that's actually an assumption that may or may not be valid, and it's also not a very robust assumption to make. So my own work has focused on coming up with auctions that do very well, even in the worst case, even without assuming anything about the agent's values. And I don't have time to tell you about that, I'm sorry. But let me just conclude by saying that this set of topics, algorithms meets game theory, is a very exciting and vibrant research area. It's only been super, super active for the last 10 to 15 years. And it used to be something that was really studied just by economists and mathematical game theorists. But the computer scientists have come into the game and actually brought quite a bit to the table that's really cool. So obviously we have new problems, such as, all these applications in internet settings. We've brought in a new set of techniques, for example, randomized auctions, approximation, reductions. We've studied these problems from the perspective of computational complexity, which you may have learned about in some undergraduate course. We've looked at other complexity issues that the economists don't tend to look at, communication complexity, how complicated it is to implement these mechanisms or algorithms in a distributed setting, and as I kind of suggested, different performance measures. And I just want to suggest, if you're interested in knowing more about this, there's this wonderful book that I have a picture of here. It's called Algorithmic Game Theory, and it kind of covers all the research topics that have been hot in the last 10 years. And I myself have written a book about game theory that just came out about a year ago. It's available for free on my webpage. And the big advantage of my book is it has lots of pictures, like these pictures below. So, with that, I'm done, and I'm happy to take questions about the technical portion.
Anna, thanks a lot. This was really great. I think everybody's going to want to run out and study game theory and algorithms now. And everybody, I'm sure, is going to be downloading your book. So this was a great talk. Thank you so much. We'll keep the chat open, so if anybody has any questions out there, please don't hesitate to put them into the chat portion. But I want to ask Anna one thing to get us started, and that is, Anna, do you, what kind of background do you have? If I'm an undergrad student and I want to, your talk just made me want to go into this as my research. I want to go to grad school and I want to study this and I want to make this my life work. What kind of background do I need during my undergraduate years and then maybe into graduate school?
Well, it's definitely true that the more math you know, the better. The most important math that comes up in this particular area, sort of there's two subjects that come up. The first and most important one is probability. And I would say probability and some basic discrete math combinatorics. Now, usually most undergraduate programs in computer science require you to take a course that introduces you to those topics. So I would strongly encourage anyone interested, well, first of all, hopefully they've taken such a course or will take such a course. But if you take such a course, which actually I'm teaching exactly that course right now, and it's a lot of fun. But if you take such a course and you find it interesting, I suggest you talk to the professor and ask them what would be the next course that goes one level deeper on this topic. And every university will have such courses. The other thing that comes up a little bit in game theory is linear algebra, but basically easy linear algebra. I would say the kind of linear algebra you do learn as an undergraduate. And again, at University of Washington, where I am, our CS majors are required to take a course in linear algebra. So the linear algebra they learn is sufficient to definitely get, certainly sufficient to read my book easily without any trouble. And I think that's kind of useful. Of course, algorithm design and analysis comes up, and those are basic undergraduate courses that you'll want to take. And then what you find is if you want to work in any area of theoretical computer science, including algorithmic game theory, you're always wanting to learn more math and more theoretical computer science, but most of that would tend to occur at the graduate level. So I think for that, it's a little bit hard for me to say specifically, but I would say you should find a professor that's willing to talk to you about that. I'm happy, if anybody wants to know more, feel free to send me email, and I could give you some additional tips on how to learn more about some of these subjects.
That's great. Great answer. We're kind of running low on time, and I don't want to miss our next topic, which is Anna's going to talk to us about what does a good grad school application look like. So I'm going to turn it back over to her, and she can then go ahead and fill us in on that. And then at the end, when Anna's finished with that, then we'll have more questions, time for more questions. So I'll turn it over to you.
Okay, thank you. And I'm sorry I ran over on the technical portion. So let's have the answer to this question, because this one's important. Are you interested in applying to a master's or PhD program? A, yes, definitely, I want to get a PhD. B, yes, definitely, I want to get a master's. C, I'm not sure yet. And D, no. If you could please answer, I would love to know, because that will help me pitch my talk. Okay, awesome. Well, I'm so happy to see that many of you are convinced and nobody said no. That's exciting. Okay, so let me just say quickly, why should you consider graduate school? These are some of the things that should be true if you're considering it. You want to solve big and important problems, you love to be creative, and you want to have a lot of independence and control over what you work on. You want to make an important, long-lasting contribution. You would enjoy being an expert, in fact, the leading expert in a particular subject. You could potentially make more money, no matter what you end up doing with this. And, of course, if you want to become a professor or research scientist, then you essentially have to do that. Okay. So I'm going to focus a little bit on applying to PhD programs, and I'm doing that mostly because that's what I know most about. But I will make comments if you're more interested in a master's program and discuss places where it might make more sense to apply to a master's program than a PhD program. So first of all, I want to say that applying to a PhD program really only makes sense if you know you want to do research and possibly teaching. If you want to be a professor teaching at a university, you usually have to get a PhD. It's not always true, I should say, very clearly, but it's definitely can be an advantage. And I should also say that it might not make sense to apply to a PhD program if you have never done research. If you have never done research, then I would consider first applying to a master's program so that you can get your toes wet with doing research, because doing a PhD, doing research is difficult. It can also be the most joyful, exciting, exhilarating thing in the world, but it can also be very frustrating. It's not the right thing for everybody, so you want to try your hand at it before you enter a PhD program. Okay. But let's say primarily that you've decided you want to apply to a PhD program. So these are the things your application will consist of. some basic info, transcripts, letters of recommendation, usually 3, statement of purpose, resume, test scores, and a fee. Now, I'm really only going to talk primarily about letters of recommendation and statement of purpose because that's the part where you might need my help with. The other part I can't really help you with or can't help too much. I mean, I will say a couple of words about grades. I think if you want to get into a really strong PhD program, then you want to have a good GPA, at least in your CS math and engineering courses. However, a very high GPA with no research experience won't necessarily get you into a really good PhD program. And in fact, having done a little bit of research is more important than having a great GPA. And I want to say this GPA I'm mentioning here is very high, and my GPA wasn't even this high when I applied to grad school, so I don't know why I have the nerve to suggest this, but I just want to say that I mean, this is what you're shooting for. Always shoot high, whatever you can do. And if your grades are not that good, that's another reason to try a master's program first because it will be a little bit easier to then move into a PhD program after you've proven yourself a little bit at the graduate level. And I also want to add about grades and classes that, you know, taking more classes is not necessarily going to help you get into a PhD program. But what might help you and might help you also get started with research is taking maybe a graduate course while you're still in undergrad. And many professors are willing to let you do that if you've had the background. So if that is an option, you should try considering that. Okay, so let me turn to the statement of purpose. So the statement of purpose is actually more of a research statement. And here is a basic outline of what you want to have. So in the first paragraph, you want to describe the general areas of research that interest you and why. And this will help the admissions committee figure out which professors should read your application. In the next few paragraphs, you will describe some of the research projects you have worked on. And by the way, I'm about to turn, after I discuss this, you can see that this is predicated on the assumption that you've done research. And you might be asking the question, how do I do research? I'm going to discuss that right afterwards. But I'm trying to make it clear that this is something you should be shooting for, and therefore you need to prepare yourself for this goal of writing such a statement of purpose. So don't worry if you haven't done any research. I'm about to tell you soon more about how to get into that. But I just want to say first a few words about if you have done research, what goes into the statement of purpose. So you want to describe what you've worked on, what problem were you trying to solve, why was it important, what approaches did you try, what did you learn, and it's completely fine if you've been unable to solve the problem you were working on. You are only an undergrad, and we don't expect you to have solved, you know, these research problems yet. The next thing you want to do is explain why you want to get a PhD. So that means reflecting on your research experiences and explaining why they were meaningful to you and what attracted you about the research. And finally, you want to explain why you're applying to this particular university. Who is it you want to work with there, and what is it about the research that you like? And to do this, you'll have to study the web pages of the faculty at that university. Okay. So, of course, the implication of this, what I just said, is that you should try to do research while you're an undergraduate if you want to do a PhD or apply to a PhD program. So how do you get a research experience? Well, you work with a professor at your undergraduate institution. You apply for a summer research internship for undergraduate or an REU. And if you simply Google REU computer science, and by the way, REU stands for Research Experience for Undergraduates, then you will find many, many opportunities. And by the way, CRA-W has our own set of opportunities for undergraduates, and we would love to have you apply for those. Those are for doing research, usually in the summer right after your junior year. And that's a fantastic way to get what you need for that statement of purpose and then also for a letter of recommendation. And finally, if you fail to I shouldn't use the word fail. If you don't manage to do a research project while you're an undergraduate, again, that's a reason to try to do a master's degree first and get the research experience while you're doing your master's. Okay, So again, as I've been implying, this will help you figure out if you actually want to go to grad school. It will give you something to talk about in your statement of purpose, and you'll get to know a professor who can write you a letter of recommendation. So how do you ask a professor to do research with him or her? So first of all, you check out the web pages of the faculty in your department, and you make a list of who might be interesting in doing the kind of work you might be interested in. And of course, it's even better if you've taken a class from someone that you really enjoyed and you get the sense that they would be a great person to do work with. That's obviously a great choice. The next thing you do is you prepare a brief summary sheet about yourself that you'll bring to the professor when you come in to ask them if they might have a research project for you. And that summary should include your photo, because professors can't remember names, but they can remember faces, your name and contact information, a brief description of your background and your research interests, if you know, a little bit about your grades and experience and skills. And when you arrive to meet with a professor, and I recommend going to office hours if you can, because that's time they've already set aside to meet with undergraduates. But if you can't do that, then just send them an email to schedule an appointment. So when you arrive, you basically explain your situation, say you're looking to get involved in research, and give him or her your summary sheet. And you should be prepared to answer, do you have any ideas about what kind of research you're interested in? They might ask you that. Which of my projects are you most interested in? And this is why you have to have looked over their web pages and recent papers before you come in, so you have some idea, like you're not completely coming in cold. And they may ask you to describe your programming background and math background. Now, I just want to say most professors don't have time, and they may not take you on. Don't give up, really. Do not take this personally. It has nothing to do with you. Most of us are just way too busy, and we may take a few undergrads on for research, but we may not have time for all the undergrads. And again, I encourage you to apply to the CRA-W programs for undergrads research. That's your best way to get going if you're having trouble finding someone at your own university. Okay, but if for some reason you're failing to find someone at your university, again, don't give up. I would say try a grad class with a professor whose research interests you. Possibly try to get to know some grad students. For example, if they're TAing your classes, you could ask them if you can help them out with something. Or find out about research seminars and group meetings and ask if you can attend. All of these are ways to get your feet wet, get to know people doing research, and potentially find research projects. Okay. And finally, let me just say, when do I think is the right time to start research? Ideally, the beginning of your junior year. And I say that because by then you know quite a bit, but you still have a good amount of time to really work on this research project. It would be great if you could work on it for a year, or at least you could work on it intensively during the summer between junior and senior year, because that will give you enough time to have something to say in that statement of purpose, and also to impress that professor so that they'll write you a great letter of recommendation. And again, as I said before, not all of us manage to do this before it's time to apply to grad school. And again, I would encourage you, if you haven't done any research, to apply for a master's program and do it at that point. It is never too late. Never, ever, ever too late. Okay. And finally, the most important part of the application are the letters of recommendation. You'll probably need 3 letters. And I do want to say that a letter that says this person did well in class is not nearly as good as one that can speak to your self-motivation, your research potential, your initiative, independence, and drive. Those are things someone who does research with you, that you do research with, can speak to. Now, often, a professor that taught a class to you can also sometimes speak to those points, but they can't speak to them very well if all they have seen is your homework and tests. So if you're trying to, I also recommend highly that you think about who you might want letters of recommendation from. And for that matter, in all your classes, try to attend office hours and talk to the professor, ask more questions, show that you're interested in going one level beyond the most basic things they're teaching in the course, and that might help them, you know, write you a stronger letter of recommendation. And lastly, I keep saying lastly, and then there's one more thing. I apologize. I'm really almost done now. Asking for recommendations. So it's awkward to ask somebody for a letter of recommendation. We all feel scared when we do that, but it's okay. And what you want to do is ask it in such a way that they will have an easy out if they're not going to be able to write you a really good letter. And so one way you could possibly phrase this is to say, do you feel comfortable writing a strong letter of recommendation for me for graduate school? And, you know, and if they don't want to, if they don't think they're going to write you a strong letter, 99% of professors will say, no, I'm not sure I feel comfortable about that. And that's fine. Don't worry about it. Move on to the next person. There's always somebody else. There are always new opportunities to get to know people and impress them and show that you're serious and that you're hardworking and that you're engaged and interested. So that's how I would recommend asking for it. Now, once they say yes, and they will, you want to give them a packet, again, containing a photo at the top because they can't remember your name. They can't associate the name with the person. The list of schools you're applying to and their deadlines. You give them a copy of your statement of purpose that's in your grad application, summary of any research projects you've done, information about your courses and grades, and anything else that might be useful for them as they're writing a letter. And keep in mind that it all sounds very daunting. I know it sounds scary to me, and I'm already a professor, but you can do it. Just one little step at a time, and you can do it. And, you know, you want to have the experience of trying out research and make sure that that's something you enjoy. And I guess my final comment is good luck with this. I know you can do it and apply for CRA-W programs. And, oh, sorry, two more things. Short advertisement. If you're thinking about applying to a PhD program, be sure to check out my wonderful university. Look how beautiful it is in Seattle. And I used the following resources when I was preparing this portion of the talk. And these are outstanding resources. I would encourage you to look at these. I especially used a document by Moore Harholbalter from CMU that basically says everything I said, but much better and in much more detail. So I'll stop there.
That was really, really important information and useful information that anybody who's going to be who's interested in grad school, and most of the participants who are listening today are interested in grad school. So thank you so much. Again, I would encourage any of the students, any of the participants who have any questions to use the chat in the bottom right-hand corner of your screen. Just type in the questions, and we'll try to ask Anna those questions. I just have a couple of housekeeping things to take care of. We're running a little short on time. Please send us your feedback. There's a URL that we'd like you to go to. This will help us in the future in planning other talks, what you thought about this talk, and what you'd like to see perhaps in the future. So I'm really asking you to help us out and do the feedback survey. And Anna was very nice about telling you about some of the CRA-W programs. Drew and CRU are our two main undergraduate research programs with CRA-W, but you can go to the CRA-W website and you'll be able to find out more information about those. All right, I think we're going to have to stop for today. Pretty much, we're going to go offline now, and we're going to. Yeah.
Can I just answer one question that I've already seen, which is,
sure.
I was asked, when should I start the grad application process? When do I ask letter writers, and when do I start writing my essay? So I did say to try to start research your junior year. Most of those things, though, the grad application process, letter writers, and writing the essay, I would say you should start at the beginning of fall of your senior year, assuming you're planning to apply to go immediately right after undergraduate. So some of what I was talking about was how do you prime the pump so that you can have people to go ask for letters and so that you can write your essay. And you need to do that background work of getting to know professors and getting to do some research. But I believe that the process of starting all the grad applications and asking the letter writers should be, September or at the latest October of your senior year, because everything is due in December, okay? Mm-hmm. You need to give your letter writers at least a month, I would say, to write the letter. And you want to write your essay early so that you can get a lot of feedback from other people, including professors, on how it's written. So hopefully that answers that question.
Great. And again, thank you so much. Your technical talk and your talk about grad school applications was really valuable and interesting information. I'm going to ask our folks at WebEx to take us offline for the video and the audio part, but we're going to stay online and do the chat. If anyone out there has any questions for Anna, please ask them in the chat box, and we'll hang on for a while until we don't see any more questions. Thank you all for participating today. Thank you for showing interest in our programs, and continue to come back for our future undergraduate research topics.